Hi everybody, this is a continuation of section 4.3, and in this video we are going to talk about dependent events and the multiplication rule for probability for the case where your events are dependent. Now in my previous video, we talked about statistical independence. In this video, we're going to talk about statistical dependent events, or statistically dependent events, say that 3 times fast, and introduce the notion of conditional probability. And if we have time, we might go on to the fundamental counting principle. Okay, so you're familiar with independent multi-stage events with replacement, where you actually draw something you draw a ball from a container, you observe it, and you put it back. And we've noticed that if you have replacement, each stage is statistically independent. With replacement, we now have dependent events. One primary example of that is if you draw one card from a standard deck of 52 cards, and then draw another card without replacement. Why are they dependent? Well, once you've drawn that one card and not put it back, you no longer have 52 cards. You have 51 cards. And the probability of drawing a certain card now is a function of how many cards you have left and the card that was previously drawn. Another example that we will use a lot is drawing a colored ball from a container, okay, and keeping that ball, because once you've done that, there's one less ball in that container, and then drawing another colored ball. Those are primary example of multi-stage experiments where one stage is dependent upon the previous stage. To beat this horse a little bit longer, let's just take a look at the event of drawing one card from a deck of 52 cards and observing that that happens to be an ace. We would call that event E, if that's what we're looking for, and then drawing another card without replacement and observing another ace. Remember, after you've drawn that one card, you only have 51 cards left. And you also only have 3 aces left. These are dependent events. And the reason why is because event E directly influences event F. And this is our multiplication rule for dependent events. Let's let E and F be 2 dependent events. Then the probability of their intersection, which is the same thing as the probability of E and F occurring, also known as the joint probability of E and F, can be written as the probability of E times the probability of F, given that E has already occurred. And we call that, well, there it is, the probability of F given that E has already occurred. We actually call this a conditional probability. Or it can be written as the probability of F times the probability of E given that F has already occurred, which is what we have here. These two terms here are what we call conditional probabilities. And here we are again. Here is the probability of E given that F has already occurred. And it looks like this. Okay? And here we have the probability of F given that E has already occurred. And we're going to work with this in a couple of fun-filled examples, which I know you're going to enjoy and will also serve you well in your homework. And let's take a look at this example. Card tricks. Here we have 2 cards are drawn without replacement from a standard deck of 52 cards. What is the probability of choosing a jack and then, without replacement, choosing a king? Okay, so we have 2 events here. The first event, E, is the event of choosing all of the jacks. Now, that happens before of them, but I'm just going to write them down as a jack. And the second event, F, is the event of choosing a king. And once again, I'm just going to write down a K here. There happens to be 4 of them. Okay, so we want to find the probability that both E and F occurred, or that E and then F occurred. Okay, that is going to be equal to the probability of E. That's going to be the easiest thing to compute first, times the probability of F given that E has already occurred. What is the probability of E? Well, we can look at that in our next slide. There it is. The probability of E is the probability of drawing all the jacks. Notice here that there are 4 jacks and there are a total of 52 cards, 13 times 4. So the probability of E is going to be equal to the number of jacks, which is 4, divided by the total number of cards, which is 52. And this can reduce to 1 over 13. Okay, now we need to figure out what the probability of F, given that E has already occurred. Okay, so here's our card deck. And then here is the scenario after one of the jacks has been taken. Notice that we no longer have 52 cards. Now we only have 51 cards because this card is gone. We still have 4 kings. Okay, so we have 4 kings, but now the size of the sample space has been reduced to 51. And this is the thing that you need to recognize in all of your conditional probability situations, or in all of your dependent situations. So it turns out that we have 4 kings, my apologies, but now we only have 51 cards. So this right here is the probability of F given E. And if that's the case, the probability that E and then F occurred is going to be equal to the probability of E, 1/13th, times the probability of F, given that E has already occurred, 4 over 51. And that will give us 4 over 663. I could write that down as a decimal to 4 decimal places, but that would not look very interesting. It'd be a very, very small number. And let's take a look at this problem here. This is the coinage conundrum, as I like to call. Suppose you keep a jar of change in your desk that contains the following. Actually, I don't have jars of change in my desk. I have Ziploc bags of change in my desk for some crazy reason. But in this scenario, here's what we have. We have 8 pennies, 12 nickels, 13 dimes, and 22 quarters. What is the probability that you reach into the jar and randomly grab a nickel and then, without replacement, randomly grab a dime? Whenever you see the word without the replacement, you need to think conditional probability. Okay, so we have here the event of choosing a nickel. I'm just going to call that I'm just going to call that N. That's the event of choosing a nickel, and then the event of choosing a dime. Okay, so the probability of choosing a nickel and then choosing a dime is going to be equal to the probability of choosing a nickel times the probability of choosing a dime given that a nickel has already been selected. Okay, that's basically what we're looking for. The probability of choosing a nickel is pretty straightforward. That is going to be equal to, well, the number of nickels. It looks a little weird, but that's how I'm going to do it, divided by the sample space. It turns out the size of this sample space is going to be 55. There are 55 coins in total. So this will be equal to 12 divided by 55. Okay, now, the probability of choosing a dime, given that a nickel has already been chosen, is going to be equal to the number of dimes that we have divided by the number of items that are left, given that we've taken a nickel. Well, the number of items that are left, given that we've taken the nickel, is going to be T minus 1. Because remember, the nickel's gone. We don't have 55 items anymore. We have 54. So this is going to be equal to 13 divided by 54. And then this will become, okay, well, the probability of choosing a nickel, 12/55. And the probability of choosing a dime, given that you already chose a nickel, 13 over 54. Multiply all that together, you will have 156 divided by 2790. I'm sorry, 2970. Notice that it's not a reduced fraction. This actually reduces to 26 over 495. If you wanted to write this to a decimal place, this would be 0.0525. 0.525. Okay, so that is how we would handle this example, the coinage conundrum. And I believe this is going to be the last example for this particular video. Okay, so in example 5, we have what we call the colored wiffle ball calamity. Suppose that we have 12 balls in a container. 6 balls are white, 6 balls are yellow. What is the probability of drawing a white ball and then without replacement drawing a yellow ball? So we want to find the probability of drawing a white ball and a yellow ball. That will be equal to the probability of drawing a white ball times the probability of drawing a yellow ball given that a white ball has already been drawn. Probability of drawing a white ball should be pretty straightforward. How many white balls? It's going to be the ratio of the number of white balls that we have divided by the total number of balls. There are 6 white balls, total number of balls is 12, and that is 1/2. The probability of drawing a yellow ball, given that a white ball has already been drawn, well, that's going to be equal to the number of yellow balls that we have. Now, since we already drew out 1 white ball, we're going to have 1 less item, so that's going to be t minus 1. That is going to be 6 over 11 for that conditional probability. In that case, then putting these together, we will have 1/2 times 6 over 11, and that will be equal to 3/11. As a decimal, that would be 0.2727. So either this answer or this answer would be acceptable. Next problem. What is the probability of drawing a white ball and then without replacement drawing another white ball? Well, that is going to be the probability of drawing a white ball and then getting another white ball. That, of course, will be equal to the probability of drawing a white ball, which we already know, times the probability of drawing a white ball given that you drew a white ball the first time. Well, we know what the probability of drawing a white ball is. That's just 1/2 in our first stage. What about the second stage? What is the probability of drawing a white ball given that you already drew a white ball? Well, if you already drew 1 white ball, that means instead of having 6 balls, you only have 5 left. So that's going to be 5. And then instead of having 12 balls, you still only have 11 left. Okay? And that would be your answer. You could almost look at this as the number of white balls minus 1, because we already took 1, divided by the total size of the sample space minus 1. In any event, this will be 5/11. And then this would round to 5 over 22. If you wanted to write that as a decimal, that would be equal to 0.2272. Okay, I believe I have 1 or 2 more problems here. Okay, this one's a little tricky. We have to pay attention to what's going on here. Suppose you draw 2 balls without replacing the first ball. Find the previous scenario. What is the probability of drawing a white ball? I guess I should have B-A-L-L there. Sorry about that. Given, this is the key word here, given that you already drew a yellow ball. What they want is the probability of drawing a white ball given that you drew a yellow ball already. So they only want the conditional probability. So this is going to be equal to the number of white balls that you have divided by the total number of balls, but remember we already drew out a yellow ball, minus 1. So here we will have 6 over 11. And that would be the answer, because all they want is the conditional probability. And continuing on, I knew I was going to do that. Now, suppose that you drew 2 balls with replacement. Since you see the word with replacement, these are independent events. Independent events. Events. There we go. When it says without replacement, dependent. With replacement, independent. What is the probability of drawing 2 white balls? The probability of drawing 2 white balls, since we have independent events, is going to be equal to the probability of drawing a white ball times the probability of drawing a white ball, which is going to be 1/2 squared or 1/4. Okay, next. What's the probability of drawing 2 yellow balls? The exact same thing. It's going to be equal to the probability of drawing 1 yellow ball times the probability of drawing another yellow ball, and that's going to be 1/2 squared or 1/4. And then finally, what's the probability of drawing a white ball and then a yellow ball? The exact same thing. It is going to be the probability of drawing a white ball times the probability of drawing a yellow ball, which is going to be 1/2 times 1/2, which is 1/4. Remember, if you see the word with replacement, they are independent events. If you see the word without replacing or without replacement, they are dependent, and you need to use the notion of conditional probability. And that is all that I have for this particular video. If you have any questions, please feel free to contact me. Stay tuned for a rather short video that will cover the fundamental counting principle. And until then, this is Bob Boyle.